presentation for today will be delivered by Stephen Lee, as you may have seen on the advertisement. Stephen is a research assistant and a Ph.D. candidate within the Universal Energy Access Laboratory at MIT. He completed a master's degree in electrical engineering and computer science and technology policy at MIT, and he received his bachelor's in material science and engineering and economics at Johns Hopkins University. So colleagues, please enjoy Stephen's presentation.
Well, thank you guys all for joining, and just express how humbling it is to be speaking in front of you guys. I know that a lot of people in the audience have a lot more experience and a lot more time thinking about load modeling than myself. So hopefully this will provide a new perspective, and I'd love to open dialogue, and please feel free to email me anytime at this email address, leesj@mit.edu. So I'm representing the MIT-Comillas Universal Energy Access Lab. We're both based out of Cambridge, Massachusetts, at MIT, and Madrid, Spain, at Comillas University. And this is, on the left, some of the people in our group, and our website's below, universalaccess.mit.edu. And some of the work that I'm presenting is not just my own. I just want to express that, but a lot of it with regards to machine learning-based demand models are. So the problem that we try to tackle in our group is that of energy poverty. And I think some of these figures shown at the top of this slide show that pretty well. 860 million people live without electricity today, and 650 will be projected without access in 2030. So even though a lot of progress will be made in the next decade or so, it's projected that we'll still fall short. And some of these charts here show the STEPS IEA scenario, which is what we anticipate areas that will be provided with electricity, and this AC scenario is what's needed. And you can kind of see in this waterfall chart, there's really a big gap between what we're planning to do and what we expect to do and what we need to do to address universal energy access. And that itself is actually only one dimension of the problem. Overall, reliability improvements and energy for growth is a larger picture as well. And this is really what we try to do in our group, is to model ways to electrify unelectrified areas of the world. So we're thinking a lot and doing a lot in the world of electrification planning, master electrification planning. And we're showing that optimization-based plans really are a new paradigm for this endeavor. So on the left here, we have traditional master plans that can take maybe 2 to 3 years to produce. They're very manual. They can cost quite a lot of money to produce these plans. And really the issue is that once you create these plans, they're not very flexible. They're difficult to update. And they really go out of date as soon as they're published or soon thereafter. So maybe about in the last decade or maybe 2 decades, the gold standard has really been GIS-based plans. It's the idea of collecting as much geotagged information into a GIS database and having sort of adaptive and more flexible plans than those that are more done by hand. But even there, it can still take about a year to make some of these plans, to collect the information necessary, and can cost about $1 million, which are some figures that show that this can be a fairly expensive endeavor and time-consuming endeavor as well. So the idea is that, well, once we get some information, once we have information of some quality, we can actually automate a lot of this process. And we have now a new paradigm, optimization-based plans that run on computer servers. They can take really weeks, days, or hours, depending on the size, and they can run at a fraction of the cost, depending on largely depending on what information is available to run them. And our group is building one of these electrification models, these optimization-based models, to do this. And you see here an example, large-scale output of our model, the Reference Electrification Model, for an area in Uganda. And these are mostly the areas that we're focused on, areas that have low energy access, rates currently. So probably not as much of South Africa, but maybe a lot of its neighbors or some areas of South Africa. And what you're seeing here is, well, first a collection of points. And each point, if you were to zoom in, represents a household on a map. And what we are given, essentially giving to the model, are this sets of points, some sort of characterized demand for each point. So demand level that might not currently be met. An indication of whether or not these places currently have electricity. And lastly, the existing network. In this case, the existing medium voltage network is shown here in black. And what the model automatically does is it decides the best, most cost-optimal combination of grid extension, mini-grid, and standalone systems to bring electricity to everyone in this landscape. And this is quite a large landscape, as you can see here on the bottom. And in blue, we have, so blue and red are grid extension clusters. Red are the medium voltage lines, blue are the low voltage. And we have similar for green, these are the mini grids. And lastly, purple show standalone systems that are prescribed to be optimal. So by grouping these customers in these ways and designing these systems automatically, we can quickly turn around, well, very detailed and implementable, well, possibly implementable plans if the information that's going into this model is of very high quality. And this model can also take into account things like topography and forbidden zones. So here we have kind of a close-up of the model over some sort of landscape. Each point is a household. The colors might be a little bit different, but the idea being that right now we're not considering the presence of this lake or some topography or forbidden zones. But in the next slide, we show that we can basically turn on these features in the model, and at very kind of high resolutions, you see that the model learns to go around lakes and to maybe do something that's sensible with regards to climbing elevation. And when you see this large scale slide that we showed before, well, if you were to zoom in, each little cluster of customers would have a design that looks a lot like this. And this can be something with very high quality input information, could be something that's indicative of a real plan that can be implemented. Under the hood, the models also optimize generation mixes and storage mixes for each microgrid that's being created. And this is over 24 hours of the day on the x-axis, and these are different days of the year that are shown in the different plots. And we have battery charging, battery discharging, solar, diesel, non-served demand. And we actually assign a cost for non-served energy so that we can optimize around this criteria as well. And there's a whole lot of economic and financial and bill of materials type information that's provided for each of these different electrification modes as well. And this is really just to say that the model goes to great lengths to produce plans and to try to be useful in ways that can actually be implemented and used as benchmarks to consider non-techno-economic facts. So the model results shown so far are really cost optimization, but we realize that there are other maybe important maybe cultural factors or other human sorts of factors that need to be included. And the idea is just to provide some sort of benchmark for real detailed plans. This slide shows that we're currently underway to scale REM to continental scales. So currently we've been doing, well, plans in a number of countries shown in red. Those shown in dark red, Rwanda and Mozambique. We actually provided national government level plans for every customer in these locations using these models. These lighter red shades are areas for which we've provided maybe district level or smaller plans. And blue is really where we're looking next, trying to find ways to amplify the reach of our models and to try to automate with the coarse level of detail, the input information that would be required to run REM for the, well, entire continent, or especially perhaps those countries with low access. This is showing a pipeline of the requisite input information to run these models. And you kind of see here, we start with satellite imagery on the left, and we have this building extraction step that finds building shapes in satellite imagery, and this load localization step that tells you exactly where households are, where the connection points may be on these building footprints. We then go into two different modules. The bottom one is electrification status estimation, trying to determine which households currently have electricity and which ones do not. The top one is demand forecasting or demand estimation. Maybe in other words, load modeling, where you're trying to do a couple of things. You can classify customers into different customer types. You can furthermore provide and infer different demand patterns that each customer type would have, or probabilistic representations of this as well. And given these inputs, demand, electrification status, building locations, we can then run our model and do validation and fine tuning afterwards. So as you can kind of see, there's a lot of input into this these electrification planning models. And the one that we're going to be talking about most today is demand forecasting. And I think that's probably what's most pertinent to the audience here. So just before we kind of dive into all of the details around demand, we're showing that our electrification model, REM, we've used that model to produce studies that motivate the need to better understand demand. And what we're finding as we're doing more and more of these planning models is that this is really the most sensitive and critical input to the model and to the eventual prescriptions that are output from that model. And essentially, if you do something if you're inaccurate in various different ways, you can actually cause a lot of inefficiencies. Or conversely, if you're more accurate, you can cause and produce a lot of efficiencies. So here we have sensitivity analyses demonstrating the criticality of estimating demand. And this came out in the IEA's World Energy Outlook in 2018. The study was also produced as a working paper. The references are shown below, but essentially we have this region of Uganda that we've been studying, and this is shown on the left here. And we have three different demand levels that are being produced or that are being run to show sensitivities for. We have a low, medium, and high case. And on the x-axis of these line plots on the right, you have that demand, the total system demand for these cases given here. And we have average costs on the top plot and grid extension shares in the bottom plot. And what we're seeing, given if we were just to follow the blue line on the top plot, I wish I could show you guys my mouse. This is homogeneous demand, and essentially what you see are large economies of scale. With very low levels of demand that are trying to be planned for, you have very high costs. In this case, something like 45 cents a kilowatt hour. And as you have medium and high demand, this drops off precipitously. Similarly, on the bottom plot, as you increase demand on the x-axis, your grid extension share increases fairly significantly from something like 0.7 to 0.95 or something in that ballpark. But it's not just aggregate total system demand that we really care about. What we also care about is understanding the heterogeneity or the sort of variability in demand profiles or customer types that are shown across the landscape. So it's not trying to just basically assign uniform consumption patterns for every household. Rather, we realize that there's very major differences between small residential households and maybe larger commercial industrial loads. And the idea is that by trying to represent this heterogeneity, we actually can produce better plans and produce plans that are lower cost as well. So these red lines show that heterogeneous demand, or representing heterogeneity over a landscape, can bring down costs because you're really targeting large loads more, and you can rely on off-grid systems perhaps more for those households with very low demands or those clusters with very low demand. And the same thing is kind of shown on this grid extension share. That story holds. As we have more heterogeneity, we rely more on off-grid technologies. We've done further studies to look at demand stimulation, and this example is a little bit contrived, but the idea is that with Sustainable Development Goal 7, we care both about universal energy access and with clean cooking technologies and the proliferation of clean cooking. And the idea here is that, well, if you can kind of see in this bottom left plot, we have multiple different cooking technologies: traditional stoves, rocket stoves, solar stoves, LPG, electric and biogas. And the idea is that most traditional stoves are very polluting. They both have very high human costs and environmental health costs, and they can cause a number of other environmental problems. And the idea is that really there's kind of two main clean cooking technologies that are viable at very large scales, both LPG and electric stoves. And the idea here is that we want to co-optimize for both universal energy access and clean cooking proliferation. And we're going to consider worlds in which we consider everyone to have clean cooking solutions. And they're either constrained between LPG stoves and electric stoves. And the idea is, on this top left plot, you can kind of see as electric cook stove penetration increases from 0 to 100%, these box and whisker plots show household level electricity costs decreasing as a distribution as you have more and more electric cook stoves. The idea is that you have economies of scale from having more and more electricity demand, and for everyone per kilowatt hour, electricity costs decrease. This dotted line shows an assumed price for LPG, and this comparison is really trying to look at the fraction of households in these box and whisker plots that are better served with electric cook stoves than LPG cook stoves. And that's all of the part of that distribution that's below this dotted line. So what we see is that, well, if we start in this right plot, top right plot here, we start off with 0% electric cook stove penetration. We have 100% of people using LPG cook stoves. You can see that for something like 40% of households, it would be better served or more cost effectively served with electric cook stoves than with LPG cook stoves. And if you were to naively just give those households electric cook stoves, you see an increase in demand, as you kind of see on this left plot over here. And what happens then is that actually more of the distribution is more cost effectively served with electric cook stoves than LPG stoves. You really just decrease costs by reaching improved economies of scale, and actually the share of households for which electric cooking is economical increases. And this feedback effect happens over and over until you see something like 80+% of households that have electric cook stove penetration. The idea here is that with jointly planning the power sector with other important economic sectors, in this case, clean cooking, but you could imagine similar arguments being made for transportation and for agriculture. Transportation with electrification of vehicles, and agriculture with the electrification of, for instance, irrigation systems or refrigeration systems or food processing systems. You see similar feedback effects, meaning that if we were to coordinate sort of planning, we can make these plans, we can reduce electricity costs and make these systems more viable for more people across the planet. So I'm going to move to the next slide. The problem that we're seeing now is that we don't know the demand in different areas at very large scales. It's generally fairly expensive to do extensive surveying or metering. And the real goal for us is to be able to generalize our demand models to larger scales than what we have maybe smart metered information for. And we're going to be relying on a lot of machine learning type tools to do that. And what I'm going to present is really a research direction that a lot of academic groups, my group included, but also groups at other universities, notably Jay Tanasia's group at the University of Massachusetts Amherst. We're all kind of moving in a direction towards this goal of generalizable machine learning models for high resolution demand estimation at large scales. And this is what I'd like to talk to you about now. So there's a couple of major things that are making this possible nowadays where it hasn't been possible as much before. The first being that the availability of satellite imagery is rapidly improving at all spatial and temporal resolutions. So we now have more satellites with cameras on them orbiting the Earth than ever before at all different scales. We have here on the top left, this would otherwise be a moving GIF, but you see that there's imagery that's taken at multiple time scales, at multiple points in time, and we now essentially have videos of the Earth as processes on the Earth evolve. Generally, there's a trade-off between high temporal resolution imagery and high spatial resolution imagery. So you can kind of see this top left plot that we have a lot of temporal resolution imagery for. High temporal imagery for is more spatially coarse looking than maybe this high resolution image on the bottom left that you can actually use and make out individual solar panels on rooftops with. This chart essentially shows that in recent years, there's been an explosion of commercial satellite launches for this purpose. At the same time, machine learning models have gotten better and better, especially those with regards to computer vision. So in this sort of famous experiment, this contest, the ImageNet contest, you have hundreds, I think actually over 1,000 of different object types that need to be recognized. And the computer model then classifies and ranks the order in which it believes these different images could be maybe a dog or a house or a person or a shoe or a plane or a car. And back in 2011, the classification error of the best systems was something like 26%. But as you get to even like 2014, 2016, this has declined dramatically as a result of improved technologies. And actually, human error is something around 5%. So for this specific use case, these machine learning models have gotten better than human expertise and human knowledge. So putting some of these things together, our group has shown that, well, we're very easily able to some degree of accuracy, determine where households are in imagery for very large regions. And this has been useful for our modeling just immediately off the bat. So before, there was field-based georeferencing. You would go around with maybe a tablet or some sort of GPS clicker, and you go house to house to collect data points on some sort of geography. And then this evolved to manual image labeling with improved satellite information. And you see that there's kind of a drop in order of magnitude of costs there. But then now there's just essentially ways to build training sets of similar sorts of manual annotations, but then train a computer model to learn from using deep learning and machine learning techniques, learn from previously annotated imagery in your training set, and then try to find similar features in imagery for which it's never seen before, so that never existed in the training set. And these computer models can do thousands of images in a couple of minutes. So they're very fast with modern computing technologies. And there's various different flavors of models that essentially do this task with different levels of training data input. And essentially, this is as far as we're concerned, a solved problem for planning, at least at some level of approximations. So we're able to find households and satellite imagery. Now, there's additional motivating examples from newer technologies that try to do more sophisticated things. In this case, on this slide, we're showing machine learning transfer learning poverty, excuse me. And what these authors have shown, so this isn't our group, but they've shown that we have high resolution SAIEE imagery for daytime imagery, but we also have slightly lower resolution nighttime lights imagery. And the idea that they've demonstrated that they can use their models to try to predict, essentially by giving as input daytime light imagery, try to predict the nighttime lights. And that's not too hard. You can imagine lights are more prevalent in areas that are more densely populated, so where there's more household, or maybe there's more lights. So generally these are street lights that are shown in these nighttime lights images. Those are more prevalent where there's more roads, perhaps, and maybe less prevalent where there's essentially just rivers or forests. But these authors did something pretty clever. They actually trained their model to predict nighttime lights imagery, but they used their model instead. They used the types of things that the model automatically learns for the task of predicting poverty. And they had data sets to try to that were more coarse and not as easily available everywhere as this nighttime lights imagery. But they were able to fit a function to try to predict with their nighttime lights models to try to predict poverty. And what they're showing in this left set of plots here is that the model is implicitly learning where rivers and streets are. It's learning where forests are. It's learning things that aren't just where people are implicitly in trying to learn this nighttime lights mapping. But they're recombining these different features that are learned in intelligent ways to try to say something about poverty. And our group is really saying this is a fantastic development. We'd love to use similar technologies that are more adapted to the problem of demand forecasting in developing countries, and that for the purpose of electrification planning. So here we're showing that, well, this is maybe another motivating example. People are using similar technologies to do crop yield prediction based on remote sensing data. So trying to understand where there's likely to be some sort of level of corn harvest in these different areas of the United States. And actually, this is interesting to us as well, because a large potential source of demand from electricity is in the agricultural sector. And if you can look at things like the color of crops or how these things change seasonally, colors change seasonally, we'd love to say something about what sorts of demand there is at these locations, and where there's potential for productive uses of energy, so that we can try to better find areas that can be more viable in terms of their electrification plans. So our group has taken some of these technologies, and we've so far used it. We've built on the general framework that other people have shown before us. And what we're showing here is using nighttime lights, building density, and transformer location data to enable electrification status estimation. This is just essentially determining where people are currently have electricity and where they do not. So on this top left figure, this shows the model architecture that we're developing. There's some sort of spatial understanding, and each node here on this grid represents a different cell. So we divide our geographic area into cells. And we can collect observations at both the region level and the cell level and try to combine them to basically form a body of auxiliary data for which we can map from the sparse survey data that we do have and learn a function actually from this data that we have lots of to some information that we only have a little bit of that we really want to get. In our case, we have a lot of nighttime lights that are shown here. So this middle plots on the top row. We have on the bottom left a plot that shows building density on the second over from the bottom left. We have some information on where different low voltage lines are. A little bit over, we have transformer locations. And in these plots on the right, we're trying to predict with higher levels of accuracy where there's electricity. And on the bottom right, we actually try to show we try to characterize the uncertainty in our estimations. So again, the top right, this is a number between 0 and 1 that says for a given household in this cell, what's the probability that that household has electricity? And in the plot on the bottom right, we show the uncertainty in our estimates. And this can be used directly in these sorts of electrification models so that we can try to understand how much, well, it would cost to electrify those households that currently don't have electricity. So this is maybe an overview. The last couple of slides are an overview of existing applications and existing models that have proven to be useful in other problems. And what we want to do is to extend these findings and then these methods to demand profiles that are likely to exist, both trying to accurately predict the aggregate level of demand, but doing, in addition to that, understanding demand heterogeneity and the possible load characteristics of neighboring households within an area. So maybe you would have a larger building that you see, and you would try to say that it's likely that this larger building is a school, or maybe it's a church or a government building or something like that. And we try to provide probabilistic representations of what those loads could be. This is just some of the input data that we've used that we're trying to feed into our models on residential demand, high school, primary school, medical center, et cetera, et cetera. Recently, we've also been starting to work with Marcus here, who's on the line, and others at Stellenbosch University on trying to incorporate similar information from the NRS Domestic Load Research Project. And these are just essentially some time series that have been pulled from that data set for a given site across South Africa. And here, this is maybe just an elaboration showing some different spatial and temporal resolution imagery. So on the right, the top right image, we here have 3-meter spatial resolution image that's been taken in March of 2016 by Planet Labs satellites. And on the bottom right, we show similar imagery for that same location taken in June 2018. And what you're able to see here in orange and purple are areas that there's been some sort of very obvious changes in greenness levels essentially in this imagery. And what we actually know about this site is that it's a tea plantation, and areas in orange in the image above are areas for which there's going to be tea bushes that are grown in the next 2 years for that location. And in the bottom plot, areas in purple show areas where there were tea plants that have now been cut. And we actually have a lot of information. It's not just various levels of greenness for these locations, because as you see in this sort of left zoom in, we have higher resolution Google Maps imagery that show that, well, this green patch is really this very neatly aligned field of rows of different tea plants. And this is at 0.6 meter spatial resolution. So while the higher spatial resolution imagery is not as temporally available, these different products can be combined in intelligent ways to say something about, well, this is very likely to be a tea plantation or some sort of maybe other crop. And there's some sort of crop rotation that's being done on this plantation, and there's some sort of output that's very easily seen just by seeing that, well, people are going in and cutting these tea plants. These are the types of signals that to us indicate that there's economic activity and demand for electricity. And just another note on this, Planet Labs, which is the company taking this right imagery, they're producing similar products for the entire world every single day. So we actually have video feeds of every meter of the planet at this resolution. We also have, so this is for South Africa, we have time series on nighttime lights imagery. And you can see that, well, South Africa got a lot brighter from something like 1992 on this top left plot to the bottom, which is, I think, showing 2013, showing that there's a lot of development. And this is another sort of time series sensor reading that's available everywhere, for which we're trying to base a lot of this auxiliary data based on. We also have aggregate consumption growth patterns. So here we have a number of different countries on the African continent, and different, on the left, this is C&I consumption per capita, and on the bottom, we have residential consumption per capita. And we see different trajectories that these countries have shown as a series, it's a time series of points, each point representing a different year. So you can kind of see South Africa has in purple here. Really, it's just orders of magnitude above a lot of other countries on the continent. And it has, well, mostly commercial and industrial demand. It's growing in some characteristic way. But if you kind of zoom in, so this is zooming into these areas, you see that, well, there's a lot of detail for countries that are just totally different magnitudes of growth. And the idea here is that we're able to say something about, well, maybe some country at some year, for instance, this is maybe just an example, but Uganda 10 years ago looks a lot like places in Rwanda today, or excuse me, Kenya today. Maybe that would be something that we could say at aggregate scales could make some sense, how these countries are growing with their consumption per capita. We also have different information on aquifer, productivity, and flow and storage type, and this is going to be used as input as well. So this is ongoing work, and the real vision here is that, well, by producing models that are able to give you different characterizations of demand or load profiles for different areas, areas for which we've never metered before, we're going to be able to do things with planning at large scales that are a lot more accurate and a lot more efficient than if we didn't have this information. And currently, a lot of electrification planners are mostly working in the dark and making some sort of assumption that they want some level of demand at some point in the future. And with these last two slides, we're showing that, well, there's different planning methodologies that can come out of this, and with different levels of demand. But I don't want to, I know we're kind of running short on time, so I'll pass over this unless there's any questions about it. And importantly, there's also the ability to do open loop, or excuse me, closed loop planning. So open loop plans are shown on the left here, where there's really just kind of a bunch of assessments, and then you come out with a plan at the end. On the right, this is showing a closed loop plan, meaning that we have some sort of prescription that comes out of our model at the end of the day. And there's actually two types of investment decisions that can be made. The first is actual electrification investments, investing in infrastructure, for instance. And the second is information gathering investments that need to be made to try to improve these models. And as more and more infrastructure rolls out and more information is gathered, those plans can then be updated and run very quickly again to try to produce plans for that next step of investment that needs to be made. So you kind of have this live version of a recommender system on what to do next and what to invest in next, both in information and in infrastructure. And lastly, we're very interested in looking at different pathways for climate effects, so climate pathways. And this is actually very dependent on demand as well. So trying to better predict demand for larger areas and estimate what demand is currently for larger areas could help us to inform decisions about whether or not to invest in infrastructure purely for development, or maybe to also incorporate some sort of environmental and climate externalities into that as well. So with that, that's my talk, and I'd love to take questions. Thank you so much for staying on the line.
Right. Thanks. Thanks, Stephen, for that informative presentation there. There is, colleagues, I think Stephen has just dropped out.
I'm still here. Can you hear me?
Oh, okay. No, it was just showing that you have dropped out here at the bottom. So there's a couple of questions that have come through, but as usual, I'll be selfish and just that by asking a question that I've noted for myself. So the model that we are using, I see that it needs data. So I think like any other model, it has to be fed data. Now,
Right.
in our context here, and you'll find that you have things called infills, where within the same settlement you've got certain households that show up after the electrification project has been done. How does this model how does it pick that up? So the settlement itself or the neighborhood itself is fully electrified, but then you find certain houses or homes in between, one or two that for some reason was never connected.
Right. So ideally, the model it's still in development, but it is being used in large areas. Ideally, the model would understand that there's a low voltage line right next to it, and you can connect at a lower cost because there's already existing infrastructure very close by. So this kind of next level of connection would be lower cost. And in practice, in a lot of cases that we look at, there's more greenfield type planning, which is a lot easier, where you just basically assume that the customers that you're connecting aren't going to be connected to that existing low voltage line, and maybe that they would then connect to a medium voltage line, or there would be a medium voltage extension to go to a new cluster. So the answer is, like, ideally, you have some sort of schedule that says there's all these different customers, and there's different costs of connecting these different customers. Those that are under the grid would have lower cost.
Okay, all right. So the next question here is from, now I'm taking questions from the chat box. So the first one was from Hilton. So Hilton wanted to know, does the model propose the strengthening of the backbone, or does it use the capacity of the existing backbone as a limit? So if, for example, you realize that what does it use as a constraint? Can it say, it will include, it will consider the new load, the forecasted load, as a limit, or does it use the existing infrastructure capacity as a limit? What does it use?
So currently, this model it doesn't do upstream reinforcements, but rather it takes in some sort of existing network. So you have information on the existing medium voltage lines or the existing low voltage lines, and you essentially have some sort of cost for electricity that currently exists on that network. And it assumes that you can just keep on pulling out power at some sort of cost per kilowatt hour, for instance, on that network. And what it does is it does this techno-economic optimization to say, well, does it make sense for this cluster of households to connect to the main grid, or rather to do an island system, a mini grid system itself? And if it can basically provide electricity to those customers cheaper than it would be to, so if it can provide electricity cheaper using mini grid technologies, then actually the costs of the amortized costs of extending the grid to the cluster and accounting for the energy costs that currently exist on the network, it would then choose to be a mini grid site, and vice versa if it's cost effective to go the other way.
Okay. I hope, Hilton, that answers your question, but then there is the next question as well, which I think it links very closely to what I was asking, still from Hilton Batman.
Okay.
It's basically asking how accurate is the extraction of cluster informal areas with shacks on top of each other. So I think you could also extend the question and say, things like high-rise buildings, how how accurate is the extraction of that information. You've got a shack on top of the other, or an informal structure on top of the other. How
Right.
accurate is the extraction of that?
So there's two answers to that. Currently, it's actually not very accurate. So but the extension to that is that it can be, and that's something that we're working on. So currently what we're doing is we're basically just extracting 2D building footprints. And we're saying that, well, for any given area in these different spatial regions, we consider that maybe a square of, a building footprint square of some size in urban area would represent a higher load than that same square in a rural area. So we're kind of getting around it, but we're not really representing this building as a high-rise building. We're looking at it as, well, a square that happens to be in a highly densely populated place. As long as we have enough demand or load consumption information for rural and urban areas, we are currently making the determination that, well, this square in the urban area will have higher demand than that in a rural area. And implicitly, potentially, this square could be a high-rise building, and that would make a lot of sense. Now, to talk about what could be done, depending on the imagery type that you have, you can see things like shadows, and you can try to infer something about exactly what these the dimensions of these buildings are, and we can be a little bit more accurate, I think, there. Hopefully that answers the question.
Okay, so then the next one is from Mike Test Barker. That's the name that's coming through there, Mike. So Mike, what he's saying is we are looking to use 10 centimeter imagery to identify PV panels, including, I don't know what that is. Are you guys aware of any work in this area? 10 centimeter imagery to identify PV panels.
So we know that people have used high resolution imagery for recognizing where PV panels are. I'm actually shocked that you're getting your hands on 10 centimeter imagery. So what's shown here on the bottom left, this is something like 30 centimeter imagery. So you can see the panels in 30 centimeter imagery. I've actually never gotten my hands on 10 centimeter imagery. I'm not even sure if that's legally available or legal to maybe like defense type personnel, if you will. And I'm sure you can see panels very crisply in resolution, imagery of that resolution, rather.
Yeah. Maybe Mike, you might want to share some of that, or you might want to engage with Stephen offline, and perhaps you have a thing or so to share with him. Then the next one is from Ted. Ted is saying that there is a lot of spatial information on record owned by government, various entities, and also it's available as well as open source. So what he wants to know is that available for use to improve the machine learning process? Is that the plan? Could that be used, that information that's available elsewhere?
And absolutely. Essentially, the models that we're building are kind of like alphabet soup. You can give it anything as a base to try to learn a function from that information to demand profiles. Or consumption profiles, rather. And if there's publicly available information from different government entities, that can be easily incorporated. We're currently using imagery from Esri and from Google Maps, but any sort of information is able to be consumed. Generally, my experience with that freely available government information is that it's lower spatial resolution, maybe higher temporal resolution, but lower spatial resolution than what you would get through maybe an Esri or Google or Mapbox or what have you.
Yeah. So now I think perhaps lastly, I saw something on slide 18.
Sure.
If you can quickly page to that, and I think one of my colleagues, I saw him here online, Sanjan. This to me looks like the first on the top right, the image there. It looks like something that we have. It's called SPC, Spot Building Count. It's a data set that is produced here locally, and I don't know the process that they go through to produce it. And I just also don't know what the cost of producing that. But I think that it's something that perhaps even, I don't know, offline you might want to engage and find out a little bit more about that. And perhaps you could use that to check your model against that as well.
Right.
And yeah, and the only the only sort of I can say issue that that okay, personally I will say in my experience I've come across is just the availability of data when you want to do something like this. The resolution that you're looking at LV data, you'll find that LV data is not available, and perhaps even the metering data is only available in certain areas at certain voltage levels. So perhaps that could be something that, the practicality of implementing a high resolution model like this, the practicality of doing that in our context, for example, where not everything is measured.
Right. That's
Yeah.
an amazing observation. Probably something I should have expanded upon. And the idea is that, well, where there's better information, you can predict with higher accuracy, with higher certainty as well, because we're characterizing uncertainty explicitly. And where you have less information, that maybe it's sparse or it just doesn't exist for these areas, you need to recognize that it doesn't exist, or that it is sparse information. And then the model can still produce maybe estimated numbers for what consumption could be, but the variance on that would be much higher. It would say essentially, we're a lot less certain about these forecasts. And actually that extends in time too. So, if we're looking at demand in the next couple of months or something like that, if we have time series for similar areas that extend until the recent past, then we can probably make pretty high certainty characterizations in those areas. But if you're looking out years, for instance, there's just no information that really supports the future as much as we have information that would support the near future. And those representations would have higher uncertainty.
Yeah. All right. Now there is just one last one. It just came through now from Vasu. Vasu wants to know do you guys have any case studies that we could look at?
So this work is still being developed. However, we have case studies for these similar problems in data fusion, and some of the examples that I've shown might be interesting for you to look at. They're looking at slightly different problems, but these are totally working systems that use a lot of the same techniques. And what we're doing, might take a little bit of time. Here we're showing the model that predicts poverty rates just based on imagery alone, and it can predict poverty rates at very high spatial resolution. This case study looks at, again, crop yield prediction at the county level, so it's a little bit less granular. And this one, which preliminary results have been published in this citation here, adaptive electricity access planning. This is looking at that electrification status estimation problem. But unfortunately, this is still work in progress and certainly not a solved problem. And actually, on that, we're very enthusiastic and looking to collaborate with people who might have data sets and expertise about areas that we actually don't ourselves from, an ocean away. So this is still ongoing work, and hopefully soon we'll be able to report.
Stephen, there is very positive feedback. People here are thanking you for the presentation. I think very, very informative. In our context, electrification will always be important. We do have green fields, and it looks like we are going to have green fields as the population grows. So you will see from the comments, there is a lot of appreciation. So we thank you so much. And colleagues, the executive committee, the attendees, thank you so much. We'll meet again in future. Thank you. Have a good evening. Bye.
Thank you, everyone.